Hello, I'm Seema and welcome to part 9 of the chapter States of Matter. We have been discussing gas laws. In this video, I'm going to tell you about the Gay-Lussac law. As I told you, there are 4 properties that can vary when we are studying the properties of gases. These 4 properties are the number of moles, pressure, volume and temperature. When 2 of these quantities are fixed, the other 2 have a relationship between themselves. And these relationships are studied as the different gas laws. In the case of Boyle's law, the relationship was between pressure and volume because number of moles and temperature were constant. For Charles' law, the relationship was between the volume and temperature because number of moles and pressure were constant. And in Gay-Lussac's law, we call it the pressure-temperature relationship, which means the number of moles and volume are constant. When number of moles and the volume of a gas are constant, at that time, what is the relationship between the pressure and temperature? That is what Gay-Lussac told us. So let us read the statement of the law now. At constant volume, pressure of a fixed amount of gas varies directly with the temperature. Constant volume is constant. Fixed amount of a gas means number of moles are constant. The pressure varies directly with the temperature. It means under these conditions, the pressure is directly proportional to the temperature. In other words, if pressure goes up, temperature goes up. If pressure goes down, temperature goes down, or vice versa. If temperature goes up, pressure goes up. If temperature goes down, pressure goes down. So we write it as P is directly proportional to T. Always remember that the different gas laws are combined later on to give us the ideal gas equation and to give us the combined gas law. Therefore, in Charles' law, I explained to you why we prefer to use the Kelvin scale. Temperature is always reported in the Kelvin scale. So we would like to, and whenever we are combining different laws and they have the same quantities, they should all be in the same units. Therefore, here the temperature is a capital T, which means that we will be reporting our temperature or we'll be using temperature in the Kelvin scale or in the absolute scale, right? So P is directly proportional to T. In order to remove the sign of proportionality, we would say P is equal to T into K, where K is the constant of proportionality. Now the constant of proportionality in the case of Boyle's law, we called it K1. In Charles' law, we named it K2. So for Gay-Lussac's law, which is the third constant, we would name it as K3. So we find from this, we can derive that P upon T is equal to K3, right? So knowing this relationship that the ratio of pressure and temperature, they remain constant, it means for a gas, if the volume is fixed and we start heating it, the temperature increases, the pressure also increases, so the ratio remains the same. It increases in such a way that the ratio remains the same. So we can just say that if a gas was at pressure P1 and temperature T1, if we change the pressure P1 to P2 at constant volume for the fixed amount of gas, the temperature would change to T2 in such a way that the ratio of P1 upon T1 should be equal to P2 upon T2. These two ratios should be the same. This is basically the Gay-Lussac's law, and this is the formula that you would be using in numerical problems. Let us just understand this. You remember when I taught you about the Boyle's law, I showed you a jar with a piston in it, and I told you that if I push the piston down and I reduce the volume of the jar to half, and I have 10 molecules, let us say, that I have drawn inside the jar. Now, those 10 molecules were exerting pressure. What is pressure? Pressure is the number of times the molecules hit the walls of the container. So that tells you the pressure. So when you reduce the volume to half, now the same number of molecules are occupying half the volume, but they are moving at the same speed because the temperature is constant. Since they are moving at the same speed, the number of times they hit the walls becomes double. So that was if you reduce the volume, the pressure is to half, the pressure doubles up. That is what I explained in the case of Boyle's law. Now in Gay-Lussac's law, the volume of the container is fixed. we have a closed container which has a certain number of molecules of a gas. And at a certain temperature, they have a kinetic energy, and due to that kinetic energy, the molecules are going and hitting the walls of the container at a certain speed, and that is measured in the form of the pressure. So for this jar at 300 Kelvin, we have this closed jar which shows a pressure of 100 kilopascals. So when we start heating this container. This closed container is heated, and when you heat it, what will happen? The molecules of the gas inside the jar, they will gain energy, and when they gain energy, they start moving faster because their kinetic energy increases. And when they start moving faster and their kinetic energy increases, the number of times, imagine when you play carom board, you have the striker, and when you strike the striker very hard, when you give it a good push, what happens? It goes and strikes the wall of the carom board, the opposite wall, comes back, hits, it just keeps hitting the walls to and fro until it loses its energy and diminishes. So when you raise the temperature, you are giving additional kinetic energy to the molecule. So what happens as a result of that? If you had the number of molecules is the same and the volume is also fixed, but the speed of the molecules is more. So won't they hit the walls faster now? So at 300 Kelvin, the pressure was 100 kilopascals. At 600 Kelvin, the pressure doubled up. That is, it became 200 kilopascals. Why? Because the speed of the molecules was now double. So if I am walking slowly and I go and touch the wall there, and then I come back slowly and I touch the wall here, and then I have my lunch, and now I have a lot of energy, so I start walking faster at double speed. So would my number of times I come and touch the walls, would it not be double too? So the pressure is nothing but the touching of the molecules of gas to the walls of the container. So what happens as a result of heating it up? The kinetic energy of the molecules increases and their speed increases, due to which they go and strike the walls of container faster. So as you raise temperature, the pressure would also increase. That is what is Gay-Lussac's law, that the pressure is directly proportional to temperature if volume is constant and for a fixed number of molecules of the gas. Now this was just understanding how it works, how this, just to explain this law to you. Now if we plot a graph between the pressure and the temperature of the gas, and we keep the volume constant, at a certain volume V1, we plot the curve, we find that it's a linear positive curve. Linear positive curve means as pressure increases, temperature increases, and we see, if you notice here, that as the pressure was this much, the temperature was this much for V1. For a higher pressure, the temperature went higher. For still a higher pressure, the temperature went still higher. So we notice it's a positive curve, and it's a straight positive curve. So it's a linear curve. So as the pressure increases, temperature increases. But there's one thing I would like you to again understand conceptually. Do you remember I had explained to you when I explained the Boyle's law that as we reduce the volume, the pressure increases at a certain temperature. If you really notice a certain temperature, let's say at this temperature, there, okay, look at these three curves, V1, V2, V3. The volume 1 is least, volume 2 is greater, and volume 3 is still greater. And what do we notice here? That as the volume decreases, the pressure increases. If you see, for V3, for this temperature, the pressure of V3 is this much. But for V2, that is a volume that is lesser than V3, the pressure is more. For V1, which has the least volume, the pressure is the highest at a certain temperature. Right? So, if you really conceptually understand it, if you took this as the constant temperature, you could still derive the Boyle's law also from this curve. But now these curves are plotted at constant volume. And again, I'd like to remind you that when we plotted curves at constant temperature for Boyle's law, we call them isotherms. When we plotted curves for constant, when the pressure was constant, we called them isobars. And when we plot curves at constant volume, they are known as isochores, spelled as I-S-O-C-H-O-R-E. So they're called isochores. So when you plot these graphs, you get isochores, and the isochores show the relationship, the direct relationship between pressure and temperature, thus showing us the Gay-Lussac's relationship, that is the Gay-Lussac's law. Now I have planned out, I want to tell you about a few examples where we see this law. During the summer months, if you notice, the tires of vehicles, which are inflated tires, we know we inflate tires with air, and these inflated tires, when they run over roads, and the roads during the summer are very hot and the atmospheric temperature is higher. So what happens as the temperature rises, the tires cannot inflate beyond that point because they're already inflated. So they cannot expand anymore. If they cannot expand anymore, what happens during the summer months? The tire bursts are more common. Why? Because as the temperature went up, the tire can no longer inflate more, which means the volume becomes fixed. So when the temperature goes higher, the volume becomes fixed. The pressure of the molecules, of the gas molecules inside the tires becomes higher. And as a result of this, what happens? The the molecules exert so much pressure, they come and hit the walls of the tire so often, and the pressure increases so much that the tire bursts. So we have more tire bursts during the summer months because of the Gay-Lussac's. You can explain it on the basis of Gay-Lussac's law. A second example here is, if you used aerosols, you would notice they always have an instruction: do not put this in flame. Store it in a cool place, right? Do not put it directly in flame. Why? Because aerosols these are cans in which gas has been pressurized, and it has been pressurized so much that it turns into a liquid. So it is behaving as a liquid under pressure. It's actually a gas which is behaving as a liquid under pressure. So why are aerosol sprays, why do these cans burst when you put them in a flame? Because the moment you throw a can into flame, it's metal, a good conductor of heat. So as soon as you throw it in a flame, the gas inside, which is already pressurized and is acting as a liquid, suddenly gains all that energy, and the pressure becomes so high that the moment you throw it into a flame, it might blast. So aerosols, sprays, they can burst when you put them in a flame. This can be explained on the basis of Gay-Lussac's law. So the third example now is that of a pressure cooker. A pressure cooker is used to cook food faster. What do you think could be the principle of a pressure cooker? What does it have? The lid seals, and it seals in such a way that no air, even air, cannot pass through it. So it's a perfect seal. And the seal, what it does, it keeps the air trapped inside the pressure cooker. So when we are cooking food in a pressure cooker, what we do, we add food and a little water to the pressure cooker. And the water starts boiling. And what is boiling? You know, what is the boiling point of water? We know it's 100 degrees Celsius. How do you explain boiling? What is boiling? Boiling is that temperature at which the gaseous state of the substance, in this case we're taking water, the gaseous state, the pressure of the gaseous state becomes equal to the atmospheric pressure. So what happens, if you notice water boiling, you will notice that when the water starts boiling at 100 degrees Celsius, at 100 degrees Celsius, the atmospheric pressure becomes equal to the pressure of the gaseous molecules which are pushing upwards. So what do we notice? Even at the bottom of the vessel, you start seeing bubbles coming from the bottom of the water. Why? Because the molecules which gain that much of kinetic energy to be gaseous, their pressure becomes equal to the pressure of the atmospheric pressure, and therefore you can see bubbles, that is gaseous molecules coming from the bottom, and that's why we see bubbles rising when the water starts boiling. Now, this happens at 1 atmospheric pressure. The boiling point of water is 100 degrees Celsius at atmospheric pressure. But what are we doing? Why does food cook faster in a pressure cooker? What is the change that we are bringing about by putting the water inside the pressure cooker? When you put water inside the pressure cooker, you have sealed the container. Now the volume is confined. The number of molecules, water molecules inside the vessel are also confined. So number of moles and volume have become fixed. So now when you raise temperature, the pressure increases. As a rule, at 1 atmospheric pressure, the water should turn into water vapor and it should escape. It just evaporates and the water starts reducing in volume. If you've noticed, when you're boiling water in an open pan, the water, it starts evaporating. You see steam coming out, and in a little while, if you keep warming the water, it'll all turn into steam and go out. But here, when you've sealed it, the pressure, as you're going on increasing the temperature, the pressure keeps on increasing. And since the atmospheric pressure is not in direct contact with this, inside the pressure cooker, the temperature of the steam may rise up to 120 degrees Celsius because we are trapping the molecules and we are going on raising their temperature. So when we do that and bring the temperature up to 120 degrees Celsius, we find that the food which was previously cooking at 100 degrees Celsius would take longer. Now at 120 degrees Celsius, the food cooks faster. So that is the principle of pressure cooker. So what is the law that we are using in a pressure cooker? We are using Gay-Lussac's law to cook food faster in a pressure cooker. Now I have planned a demonstration for you too, but for that I'll have to take you to the kitchen. So just one more demonstration to explain Gay-Lussac's law. Bear with me, I'll be back in a minute. So here's the demonstration that I have planned for you. I have this can of soda which is opened and I have kept it over a flame. If the can had the soda inside it, then it would have carbon dioxide which has been pressurized to give you the fizz. And if I had raised the temperature at that time, the can would have bursted just as any can of aerosol would, because the gas which has been pressurized inside, as a result of heating, it would gain pressure, and due to the pressure it would hit the walls of the can and the can would burst. But now I have removed the soda from this, and I have removed, that is, it's an open can, and I drank the Coke also, so that we don't have any mess here. Now I'm going to raise the temperature of the can, and I have an ice bath here. So let's see, when you raise the temperature of the can, the air present inside, it gains energy and it expands. When it expands, the air, it comes out of the can. So when the air comes out of the can, the pressure inside the can of the gas decreases as a result of increased temperature. That was Charles' law. Now, what I'm going to do for Gay-Lussac's law, what I need is that the volume should be constant. So what I'll do, I'll take this can once it is heated and the volume, the pressure inside is less, and I'll plunge it into this ice bath. When I plunge it inverted, the opening is also going to be sealed by water. So the volume would become fixed, and the pressure inside at a higher temperature, the pressure of the gas inside the can, it remains whatever the pressure was. When you invert it, let us see what happens. The atmospheric pressure is much higher while the pressure of gas inside the can is much lower. As soon as you lower the temperature, what is it that should happen? The volume of the gas inside, or rather due to the decrease in pressure, let us observe what happens. I'll start heating it now. Now the gas inside the can is evaporating and is at a higher temperature. Now we're going to invert it into a water bath, an ice bath. Do you notice? Do you notice? It just squeezed. This is what is left of the can. It is the pressure outside, the atmospheric pressure was so much higher that it pushed the can, the walls of the can inside, because the pressure inside the can of the air was so low. And you can imagine what an impact that can have on a can in which the pressure of the gas is less. As soon as the molecules of air trapped inside the jar, they got cold, the pressure inside became so low that the external pressure squeezed the can. So this is also based on Gay-Lussac's law. So these were my demonstrations and my demonstration, and this was about Gay-Lussac's law. In the next video, I'm going to solve a few numerical problems on Gay-Lussac's law. I hope you liked the video. If you liked it, please give it a thumbs up. I would appreciate that. Subscribe to my channel, share my videos with your friends, and please keep returning for more videos in chemistry. Thank you, and bye-bye for now.